In April 2011, in Mobile, Alabama, an American aviation bedrock was quietly dismantled. Teledyne Continental Motors, the company that had effectively taught the United States how to fly, was sold to a Chinese state-owned aerospace conglomerate. For decades, Continental's horizontally opposed piston engines were the undisputed pulse of American general aviation. If a pilot learned to fly in a Cessna 150 or cross the country in a Beechcraft Bonanza, they trusted their life to a Continental block. But the sale meant that the thousands of mechanics turning wrenches on these aluminum engines in Midwestern hangars were now maintaining a machine owned by a foreign superpower. The paradox was unmistakable. The machine had not failed. The engines still fired up on command. But the American business model that sustained them could no longer survive product liability, aging pilot rosters, and the crushing cost of modern aviation. The real story of Continental is not just a corporate buyout. It is the story of how an engine democratized the American sky, and what happened when the air became too expensive for the people who built it. Every week, we tell the stories of American engines, factories, machines, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place in Detroit, Michigan in 1931. In 1931, the American sky was a heavily restricted frontier. If you wanted to leave the ground, you generally needed to be a military aviator, a daredevil, or a very wealthy man. Aviation was dominated by massive radial engines, aircraft engines with cylinders arranged in a circle around the crankshaft, which produced immense power but cost a fortune to manufacture, operate, and maintain. On the other end of the spectrum were heavy, unreliable, liquid-cooled inline engines left over from the First World War. They leaked coolant, they cracked under thermal stress, and they required constant attention from specialized mechanics. Flying was not an industry for the middle class. It was a spectacle. But down on the ground in Detroit, Michigan, Continental Motors was facing its own crisis. Founded in 1905, Continental had spent 2 decades as a powerhouse of the American automotive industry. They were a proprietary engine builder, supplying internal combustion engines, machines that burned fuel inside their cylinders to create power, to dozens of independent car brands. But as the 1920s closed, the automotive market began to consolidate. Giants like Ford and General Motors were casting their own engine blocks. Continental's traditional customer base was vanishing. To survive the Great Depression, Continental had to find a new place to put its iron and aluminum. They looked away from the deteriorating roads of the early 1930s and looked toward the sky. The breakthrough did not come in the form of a massive, roaring military power plant. It came in a small, unassuming 4-cylinder machine called the Continental A40. Introduced in 1931, the A40 was a revelation in simplicity. It was a horizontally opposed engine, a design where the cylinders lay flat, punching horizontally away from a central crankshaft. This architecture lowered the center of gravity, fit neatly inside a narrow aerodynamic nose, and naturally canceled out much of the harsh vibration that plagued other small engines. More importantly, it was air-cooled. An air-cooled engine sheds internal heat directly into the rushing slipstream using thin metal fins cast into the cylinder heads and barrels. By eliminating the radiator, the water pump, the hoses, and the heavy liquid coolant, Continental stripped away dozens of potential failure points. The A40 displaced just 115 cubic inches and produced a modest 37 horsepower. By modern standards, that is barely enough output to run a heavy-riding lawnmower. But in 1931, 37 horsepower was exactly what the American aviation market needed. At the same time, in Bradford, Pennsylvania, an aviation pioneer named C.G. Taylor and an oilman named William Piper were trying to sell a lightweight, fabric-covered airplane called the Piper Cub. The airframe was brilliant, light, forgiving, and cheap to build. But early models were severely handicapped by a lack of reliable power. The engines they tried were either too heavy, too expensive, or prone to rattling themselves apart mid-flight. Then they bolted the Continental A40 to the nose of the Cub. The pairing of the Taylor Cub, later the legendary Piper Cub, and the Continental A40 changed the trajectory of American transportation. The A40 was incredibly reliable, inexpensive to manufacture, and simple enough that automotive mechanics could quickly learn how to service it. The engine allowed Piper to sell an airplane for around $1,300 in the mid-1930s, essentially the price of a mid-range automobile. Suddenly, the sky was democratized. Small grass airstrips began to appear on the edges of Midwestern farm towns and rural pastures. Flight schools opened. A new class of American user emerged, the civilian private pilot. The A-40 taught Continental how to build for the air, but the market demanded more power. As the 1930s progressed, Continental refined the horizontally opposed architecture. They introduced the A-50, and then, the engine that would permanently cement their name in the sky, the Continental A-65. Producing 65 horsepower, the A-65 became the definitive power plant of the Piper J3 Cub. It was an engine defined by absolute mechanical honesty. It utilized dual magnetos, engine-driven electrical generators that provide spark for ignition. Because a magneto generates its own electrical current independently of the aircraft's battery, a Continental A-65 would keep firing as long as the internal components kept turning, even if the entire electrical system of the airplane failed. This was not a convenience feature. It was a requirement for survival. If an automotive engine fails, a driver pulls over to the shoulder. If an aircraft engine fails, the pilot is immediately forced to turn the airplane into a glider and find an emergency landing field. Continental understood that they were not just selling horsepower, they were selling the promise that the propeller would not stop turning. The sound of the A-65 became the soundtrack of rural American aviation. Starting one was a physical ritual. Without heavy electric starters, early pilots had to hand-prop the engine. A mechanic or a pilot would stand in front of the aircraft, grasp the wooden propeller, and pull it downward with a sharp snap to rotate the crankshaft, the rotating shaft that turns piston motion into rotational power, forcing the engine to draw in fuel and fire. When the A-65 caught, it produced a distinct rhythmic bark. It idled with a mechanical clatter that settled into a steady, comforting drone once the throttle was pushed forward. That drone would soon be heard across the entire country. As World War II loomed, the United States government realized it faced a massive shortage of military aviators. In 1938, they launched the Civilian Pilot Training Program to rapidly teach thousands of young Americans how to fly. The aircraft chosen for the bulk of this training was the Piper J3 Cub, powered almost exclusively by the Continental A-65. Before they ever touched the throttle of a massive Pratt & Whitney radial in a bomber or an Allison V-12 in a fighter, hundreds of thousands of American pilots learned the fundamentals of flight behind a small flat-four Continental engine. Continental had successfully shifted its identity. They had abandoned the declining automotive supplier market and built the foundation of American general aviation. The A-40 and the A-65 proved that an engine could make flight affordable. Now Continental had to prove it could make flight in American industry. When World War II ended in 1945, thousands of American military pilots returned home. They brought with them a habit of flight, a comfort with altitude, and a desire to keep flying. Bolstered by the GI Bill, which paid for civilian flight training, the American general aviation market exploded overnight. Between 1945 and 1947, tens of thousands of light aircraft rolled out of assembly plants. Continental was perfectly positioned for this peacetime boom. They had spent the late 1930s and the war years refining their horizontally opposed engine family. While large commercial airliners and military bombers relied on massive radial engines, piston aircraft engines with cylinders arranged in a circle around the crankshaft, the light aircraft market needed something entirely different. A radial engine was a maintenance heavyweight. It required complex oiling systems, suffered from immense aerodynamic drag, and obscured the pilot's forward visibility on the ground. Continental's O-series engines, where the O stood for oppose, solved all of these problems. By laying the cylinders flat, Continental allowed aircraft designers at Cessna, Piper, and Beechcraft to build sleek aerodynamic cowlings that pilots could easily see over while taxiing down a runway. The breakthrough that cemented Continental's absolute dominance came with a specific pairing, the Continental O200 engine and the Cessna 150. Introduced in the late 1950s, the O200 was a four-cylinder, air-cooled engine producing 100 horsepower. Its displacement, the total volume swept by the pistons inside the cylinders, was exactly 201 cubic inches. It was not a glamorous piece of machinery. It was not designed to break speed records or push the boundaries of high-altitude performance, but it possessed something far more valuable to the American aviation market: extreme, repeatable predictability. The Cessna 150 quickly became the definitive American training aircraft, and the O-200 was its beating heart. In flight schools across the country, this engine was subjected to the most brutal operating conditions imaginable. Student pilots shock-cooled the cylinders by descending too fast. They fumbled the fuel mixtures, and they bounced the airframes hard onto asphalt runways. Yet the Continental O-200 simply kept running. This durability was not magic. It was the result of a deliberate, conservative engineering philosophy. Continental over-engineered the block, the main engine structure that holds the cylinders and major internal parts, and intentionally understressed the internal components. They kept compression, the squeezing of the fuel mixture inside the cylinder before combustion, relatively low. But a reliable block was only half of the equation. Continental's true breakthrough was in building a service network that covered every corner of the United States. An aircraft engine does not live in isolation. It relies on a highly regulated system of maintenance. In the United States, this work is performed by an A&P mechanic, a technician certified by the Federal Aviation Administration to work on airframes and power plants. Continental made sure that every A&P mechanic in America knew exactly how to work on their engines. They distributed exhaustively detailed service manuals to every local hangar, flight school, and repair station. When a Continental engine reached its TBO, or time between overhauls, a federally recognized metric dictating when an engine must be removed from service for major maintenance, the process was a known science. In a Midwestern hangar and overhaul, a major service process where an engine is taken apart, inspected, and rebuilt to operating standards, was a heavily documented ritual. A mechanic would pull the engine from the firewall, split the aluminum crankcase, and measure the crankshaft, the rotating shaft that turns piston motion into rotational power, down to the 10,000th of an inch. Continental flooded the market with replacement cylinders, pistons, gaskets, and bearings. If a mechanic at a small rural airstrip in Iowa needed a part for a Continental O-300 straight six, a six-cylinder engine arranged in one line, he could have it in days. Every bolt on the engine was tightened with a torque wrench and then secured with stainless steel safety wire to ensure that engine vibration could never back a fastener out in flight. This system of parts, manuals, and mechanics created a firewall of trust. Pilots trusted the engine because mechanics trusted the engine. To understand this trust, one must look at how these engines were fed. Most early Continental engines utilized a carburetor, a device that relies on engine vacuum to mix liquid fuel and air before the mixture enters the cylinders. While simple and reliable, carburetors in aircraft are highly susceptible to carburetor ice, a condition where the temperature drop inside the device causes moisture in the air to freeze, potentially choking off the engine. Pilots had to meticulously manage carburetor heat controls during flight, but Continental's design was so well understood that managing its quirks became second nature to the American pilot. It was a mechanical dialogue between the human in the cockpit and the iron behind the propeller. Having conquered the flight training market, Continental scaled up. If the O-200 was for learning, the O-470 was for traveling. A six-cylinder, horizontally opposed engine producing up to 230 horsepower, the O-470 became the engine of choice for the serious American private pilot. When Beechcraft needed a power plant for their legendary V-tail Bonanza, they bolted a Continental engine to the nose. Cessna used the O-470 in the 180 and 182, turning them into backcountry workhorses that could carry heavy loads into short dirt, gravel, or grass strips in Alaska and the American West. The O-470 proved that Continental's flat engine architecture could scale up to meet the demands of business executives, bush pilots, and regional freight haulers without losing its fundamental reliability. The architecture was set. The service network was built. Continental was no longer just an engine maker. It was the pulse of the American sky. By the late 1960s, American general aviation was no longer just a post-war hobby. It was a sprawling, highly lucrative industrial machine. Businessmen were flying themselves to meetings. Doctors were flying to remote rural clinics. Farmers in the Midwest were using light aircraft to survey hundreds of acres of crops in a single afternoon. and powering a massive percentage of this airborne economy was Continental. To meet an unprecedented surge in demand, Continental needed absolute scale. In 1966, they moved their primary aircraft engine production out of their crowded northern facilities and established a massive manufacturing hub in Mobile, Alabama. 3 years later, in 1969, the company was acquired by the industrial conglomerate Teledyne, officially becoming Teledyne Continental Motors. The Mobile factory became a fortress of American aluminum and iron. Inside, foundries poured molten metal into sand molds to cast engine crankcases and cylinder heads. Machining lines, where raw castings are cut, drilled, and ground down to exact tolerances, ran virtually around the clock. The factory floor smelled of cutting fluid, hot metal, and assembly grease. They were not just building replacement parts, they were mass-producing the American right to the sky. But as the market matured, pilots demanded aircraft that could fly higher, faster, and carry heavier payloads. The old carbureted engines were remarkably reliable, but they had reached their performance limits. Continental's answer was the IO series. The I stood for injected. Continental fully embraced fuel injection, a system that sprays fuel directly into the engine's intake ports more precisely than a carburetor. This technology fundamentally changed how American pilots flew. It entirely eliminated the deadly risk of carburetor ice. It allowed engines to produce more power, run smoother, and consume fuel far more efficiently at high altitudes. The crown jewel of this era was the Continental IO 520. It was a massive, naturally aspirated six-cylinder, horizontally opposed engine, displacing 520 cubic inches and producing up to 300 horsepower. When Beechcraft needed a power plant for their premier six-seat business aircraft, the A-36 Bonanza, they chose the IO 520. When Cessna built the 210 Centurion, a high-wing workhorse designed to cruise at nearly 200 miles per hour, they bolted an IO 520 to the firewall. The sound of an IO 520 starting up on a busy tarmac was unmistakable. It did not have the staccato clatter of the old four-cylinder trainers. It fired with a deep, resonant bark that quickly smoothed out into a low, muscular hum as the propeller pulled the airframe forward. For an American businessman or a charter pilot in the 1970s, that sound meant you were going exactly where you needed to be, on your own schedule, without waiting for a commercial airline. The sheer scale of this empire is difficult to comprehend today. In 1978, the American general aviation industry manufactured over 17,000 light aircraft in a single year. That was not a decade-long total. That was a 12-month production run. And a staggering percentage of those aircraft rolled out of the factory doors in Wichita, Kansas, and Vero Beach, Florida, with a Teledyne Continental engine under the cowling. To support those 17,000 planes a year, an entire shadow economy of service had to expand across the country. Continental engines required specialized aviation spark plugs, specific ashless dispersant oil, intricate magnetos, and thousands of replacement cylinders. Every major airport and almost every small county airstrip had a maintenance hangar that functioned as an authorized piece of the Continental Empire. Parts catalogs, thick as phone books, sat on oily workbenches from California to Maine. If a pilot landed in rural Nebraska with a leaking cylinder gasket, a mechanical seal that prevents fluid or pressure loss between engine parts, a mechanic could have the replacement shipped overnight from a distributor. The factory in Mobile was pouring aluminum as fast as the market could buy it, but building a powerful engine was only half the battle. Keeping it in the sky required an American culture of absolute, uncompromising trust. By the mid-1970s, the smell of an American general aviation ramp was defined by 100 LL, a high-octane, leaded aviation gasoline dyed blue to distinguish it from automotive fuel. It burned through Continental engines by the millions of gallons. As the market expanded, American businessmen and regional fleets demanded more capability. A single engine was fine for daytime flying, but crossing the Rocky Mountains or flying over the Great Lakes at night required redundancy. The industry turned to light twin-engine aircraft, and Continental provided the power. The Cessna 310, with its aggressive profile and wingtip fuel tanks, relied on a pair of Continental engines. The Beechcraft Baron utilized two massive Continental IO 520s, sinking the propellers of a twin-engine aircraft, the physical act of a pilot adjusting the throttles and propeller levers until the harmonic thrum of the two Continental blocks merged into a single, continuous, vibration-free drone, was a sensory hallmark of American corporate travel. It was the sound of a thriving industrial economy. To push these aircraft even higher, Continental aggressively developed turbocharging. A turbocharger, a device driven by exhaust gases that forces more air into the engine, solved a fundamental problem of aviation. As an airplane climbs, the air becomes thinner, and a naturally aspirated engine loses power. By bolting a turbocharger to the IO 520, creating the TS-C20, Continental allowed an engine to maintain its maximum sea-level horsepower all the way up to 20,000 feet. This transformed American private aviation. Suddenly, an owner pilot in a pressurized aircraft like the Cessna P210 Centurion could climb above the turbulent weather, riding smooth air currents across the country at over 200 miles per hour. It was no longer just a hobby, it was a personal airline. The factory in Mobile, Alabama, evolved to meet this highly technical demand. Building a turbocharged aviation engine required extreme metallurgical precision. The exhaust gases driving the turbocharger could reach 1,600 degrees Fahrenheit, requiring specialized heat-resistant alloys for the exhaust valves, the mechanical doors that let spent gases out of the cylinder, and the turbine wheels. American machinists cut cylinder barrels, honed steel liners, and dynamically balanced crankshafts so perfectly that a six-cylinder engine could run at maximum continuous power for hours without shaking the airframe. In 1978 and 1979, the industry reached its absolute zenith. General aviation manufacturers delivered roughly 17,000 light aircraft in a single year. The mobile factory was operating at a staggering pace, casting, machining, and assembling engines to feed assembly lines in Kansas, Florida, and beyond. To maintain this massive fleet, the service network had to be flawless. In a rural Kansas maintenance hangar, a Continental engine was not treated as a disposable appliance. It was a rebuildable industrial asset. An A&P mechanic would stand beneath the cowling, referring to a heavily thumbed, oil-stained Teledyne Continental service manual. They would follow step-by-step procedures for setting magneto timing, the precise calibration of when the electrical spark fires in relation to the piston's position in the cylinder. This timing was the difference between a smooth-running power plant and one that could destroy itself in flight from pre-ignition. In an America where an engine could decide whether a rural patient reached a hospital, a farm received its emergency parts, a regional executive made the meeting, or a student pilot learned to command the sky, power was not an abstraction. It was iron, fuel, labor, heat, sound, repair, and trust. For decades, Continental had held up its end of that trust. A pilot knew that if they properly managed the fuel mixture, adjusting the ratio of fuel to air as the aircraft climbed, the Continental block would not quit. A mechanic knew that if they adhered strictly to the service bulletins in overhaul intervals, the aluminum and steel would hold its compression. It was a closed, perfectly functioning ecosystem of American manufacturing, dealer support, and mechanical competence. The Teledyne Continental badge was quite literally bolted to the front of the American dream of flight. But this entire empire was built on a series of fragile assumptions. It assumed that 100 watt aviation fuel would remain cheap and politically acceptable. It assumed that the pipeline of young Americans wanting to fly would remain full. And, most importantly, it assumed that the legal and regulatory framework of the United States would continue to treat aviation as an inherent risk managed by pilot skill. Continental had conquered the American sky, but the machine had not solved what would happen when the world on the ground began to change the rules. The first crack in Continental's absolute dominance did not happen on a runway, in a factory, or in the sky. It happened in an American courtroom. By the early 1980s, the general aviation boom hit a sudden, invisible wall. The problem was not the engineering. The Continental engines rolling off the line in Mobile, Alabama, were the most refined, reliable piston aircraft power plants the company had ever built. The iron and aluminum were solid. The system around them, however, was beginning to fracture under the weight of product liability law. In the United States, aircraft and engine manufacturers became subject to strict liability. This meant that if a 20-year-old airplane crashed, the manufacturer could be held financially responsible, regardless of how well the machine was originally built. In aviation, the harsh reality is that pilot error, flying into severe weather, mismanaging the fuel mixture, or simply running out of gas, causes the vast majority of accidents. But a pilot's estate rarely had the money to pay out a major lawsuit. A massive industrial conglomerate like Teledyne Continental Motors, however, had deep pockets and comprehensive insurance. Almost overnight, Continental and the airframe manufacturers they supplied were flooded with litigation. Every time an aging airplane went down in a farm field or short of a rural runway, the engine maker was sued. The cost of defending these lawsuits and paying out settlements had to be factored into the price of every new engine and every replacement part sold. This legal environment fundamentally broke the economics of American flight. To cover liability reserves, the cost of a new light aircraft skyrocketed. A four-seat airplane that an American middle-class family could reasonably finance in 1975 became an unattainable luxury by 1985. Sales plummeted. Then came the shock that permanently altered the industry. In 1986, Cessna, the undisputed giant of American general aviation and Continental's most vital partner, made a staggering decision. Facing insurmountable liability costs, Cessna completely halted the production of all single-engine piston aircraft. The assembly lines in Wichita, Kansas, went quiet. The pipeline that had absorbed thousands of Continental engines a year was suddenly severed. Back in Mobile, the impact was immediate and devastating. The foundries and machining lines that had been running at maximum capacity just a decade earlier were forced to drastically scale back. Continental went from mass-producing engines for a booming national industry to building a trickle of new blocks while largely surviving as a replacement part supplier for the existing fleet. The scale that had made the American aircraft engine so profitable had evaporated. This collapse in new aircraft production triggered a chain reaction throughout the service network. Because fewer new pilots were learning to fly and fewer new airplanes were entering the market, the specialized infrastructure required to maintain a Continental engine began to shrink. Small independent flight schools at rural Midwestern airstrips started to close. When an older A&P mechanic, a technician certified to work on airframes and power plants, retired, there were fewer young mechanics stepping in to take their place. The intricate knowledge of how to properly time a magneto or adjust a carburetor on a Continental O200 slowly began to leave the American workforce. As the 1990s approached, a second systemic threat emerged: fuel. For decades, the high-performance engines in Continental's IO 520 and TSCO 520 series relied entirely on 100LL, a heavily leaded aviation gasoline. The lead was not there for performance, it was there to prevent detonation. Detonation is a catastrophic engine condition where the fuel-air mixture explodes violently and prematurely inside the cylinder. Rather than burning smoothly, in a high-compression, air-cooled aircraft engine operating at high altitudes and extreme temperatures, lead was the only cheap, reliable chemical barrier, keeping the engine from destroying itself. But down on the ground, the American automotive industry had already transitioned to unleaded fuel and catalytic converters. The Environmental Protection Agency began looking toward the sky. The regulatory pressure to ban leaded aviation fuel introduced massive uncertainty into the market. Continental's engineers knew that designing a high-output, air-cooled engine to run safely on unleaded fuel was a monumental challenge. It required redesigning cylinder heads, lowering compression ratios, and integrating complex electronic engine controls, investments that cost millions of dollars. But how could a company justify massive research and development spending when the market for new aircraft was a fraction of what it had been in 1978? The engine was caught in a trap. The old architecture was too reliable to throw away, but the legal, economic, and environmental world around it was making it increasingly difficult to sustain. The block was still strong, but the foundation of the empire was starting to give way. As the 1990s bled into the 2000s, the shrinking manufacturing base triggered a demographic crisis on the ground. The problem was no longer just the legal cost of building a new airplane. It was the cost of keeping the old ones in the sky. Because Cessna and Beechcraft had virtually stopped mass-producing entry-level aircraft, the American general aviation fleet began to rapidly age. The Cessna 150s and Piper Cubs that had once democratized flight were now 30, 40, or 50 years old. And as the airplanes aged, so did the people flying them. The barrier to entry for a young American wanting to earn a pilot's license had become astronomical. Flight schools had to charge exorbitant hourly rates just to cover their own insurance premiums and the rising cost of 100 lateral aviation fuel. General aviation slowly morphed from a middle-class utility into an upper-class luxury. This demographic collapse fundamentally undermined the service network. For decades, the Continental engine was kept alive by a massive, decentralized army of A&P mechanics. But as the fleet shrank and older mechanics retired, fewer young technicians were entering the field to take their place. The physical act of maintaining a Continental engine is a highly specialized trade. It requires understanding analog mechanical systems that modern automotive mechanics no longer see. Properly adjusting a mechanical fuel injection system on a Continental IO 520 or safely pulling a heavy steel cylinder barrel off an aluminum crankcase without damaging the piston rings requires a deep, tactile familiarity with the machine. As the seasoned mechanics left the hangars, that institutional memory went with them. In many rural American airstrips, the local maintenance shop simply closed its doors. If a pilot needed a major overhaul, they increasingly had to fly the aircraft hundreds of miles to a specialized regional shop. The economics of the overhaul itself were also breaking down. In 1975, rebuilding a Continental engine was a routine, manageable expense. By the 2000s, the cost of parts, labor, and liability insurance meant that a factory-rebuilt Continental engine could easily cost $30,000 to $40,000. If the aging airframe it was bolted to was only worth $50,000 on the open market, the owner was trapped in an impossible financial equation. Thousands of perfectly sound airplanes were pushed to the back of grass tie-downs, left to slowly corrode under tarps because the cost of spinning the Continental block back to life was too high. Back in Mobile, Alabama, the factory was caught in this exact same trap. Teledyne Continental Motors was still casting aluminum, machining crankshafts, and assembling some of the finest piston aircraft engines in the world. But they were operating in a market that had fundamentally lost its scale. They were no longer the vanguard of a booming American transportation network. They had become curators of a legacy fleet. For the parent company, Teledyne Technologies, the aviation division increasingly looked like an anomaly. Teledyne had evolved into a massive conglomerate focused on high-margin digital imaging, aerospace electronics, and defense systems. A factory pouring molten aluminum to build heavy, air-cooled piston engines that burned leaded fuel was a low-margin, high-liability outlier in their corporate portfolio. The environmental pressure to eliminate 100 LL avgas only deepened the uncertainty. The American financial markets no longer saw a profitable future in piston-powered flight. The final fracture occurred in April 2011. It was not a sudden bankruptcy. It was not a dramatic factory closure. It was a quiet, calculated corporate divestment. Teledyne announced that it was selling Continental Motors. The buyer was not an American competitor, an American private equity firm, or a resurrected American aviation giant. The buyer was Avic International, the aviation industry corporation of China, a massive state-owned aerospace conglomerate based in Beijing. They purchased the entirety of Continental Motors for $186 million. For an engine company that had once powered the civilian pilot training program, pushed tens of thousands of American veterans into the sky, and built the mechanical foundation of Cessna and Beechcraft, the sale was a profound psychological shock to the American aviation community. The Mobile, Alabama factory remained open. The American workforce kept machining parts. The engines rolling off the line still looked, sounded, and performed exactly like the blocks that had built the industry. But the ownership, the profits, and the ultimate control of the intellectual property had permanently left American shores. The paradox was absolute. The engine itself had never failed. The horizontally opposed architecture was still the most reliable way to power a light aircraft. But American capital had decided that the American sky was too legally, environmentally, and demographically expensive to sustain it. The engine still ran. The block held its compression. The liability costs climbed. The flight schools closed. The local mechanics aged out. The American ownership ended. The badge remained. The world that built it was gone. The Chinese acquisition in 2011 did not erase the Continental engine from the American sky. Today, the company, rebranded as Continental Aerospace Technologies, still operates the factory in Mobile, Alabama. They still cast aluminum, they still build horizontally opposed piston engines, and they still supply the global aviation market. But the true legacy of the American Continental Empire is not found in a corporate boardroom or on a modern assembly line. It is found in the tens of thousands of aging airframes still tied down at municipal airports across the United States. The American general aviation fleet is overwhelmingly old. The Cessna 150s, the Piper Cubs, and the Beechcraft Bonanzas that democratized flight in the mid-20th century are now 40, 50, or 60 years old. And because replacing them with new aircraft is financially impossible for most pilots, the engines bolted to their firewalls have been forced into an indefinite industrial afterlife. This is not nostalgia. A restored muscle car V8 in a garage is a weekend toy. A Continental 0470 powering a Cessna 182 in the Alaskan backcountry, or a Continental IO 520 pulling a cargo plane over the Rocky Mountains, is a highly regulated, life-dependent survival tool. These engines cannot simply be replaced by an electric motor, a hybrid battery system, or a modern automotive block. The Federal Aviation Administration's strict certification process makes swapping unproven technology into an existing airframe so prohibitively expensive and legally complex that keeping a 50-year-old Continental block alive is often the only financially viable way to keep the airplane flying. The machine remains because the system demands it. To keep this massive legacy fleet in the air, a shadow industry of specialized overhaul shops and independent mechanics has evolved. When a Continental IO 520 reaches its time between overhauls, often 1,700 flight hours, it is not thrown away. It is removed from the aircraft and shipped to a specialized rebuild facility in places like Tulsa, Oklahoma, or rural Texas. There, the aluminum crankcase is split apart. The steel crankshaft is magnafluxed, a process where the metal is inspected with magnetic particles under ultraviolet light to find microscopic cracks. The cylinders are honed, the valves are reseated, and the block is industrially resurrected. The true custodians of this empire are the American A&P mechanics. Go to the massive EAA AirVenture fly-in at Oshkosh, Wisconsin, or walk into any small-town maintenance hangar on a Saturday morning. You will find an aging generation of mechanics passing down the tactile, analog knowledge of how to keep these engines alive. They do not plug laptops into an OBD2 port to diagnose a problem. They use heavy, oil-stained Teledyne Continental service manuals that have sat on workbenches for decades. They diagnose a rough idle by listening to the exact sound of the exhaust. They read the carbon deposits on an aviation spark plug to understand the fuel mixture. They use specialized pliers to twist stainless steel safety wire around the heads of bolts, ensuring the relentless vibration of the flat-4 architecture never backs a fastener out in flight. It is a deeply physical relationship with a machine. Here is the strange footnote to the Continental story. If a young American teenager walks into a local flight school today to begin training for their private pilot certificate, they will likely climb into a Cessna 152. The dashboard might be retrofitted with brilliant modern glass panel displays, GPS navigation, and software-controlled radios. But when they turn the key, the machinery pulling them into the sky is a Continental O200 that was engineered during the Cold War. The avionics belong to the 21st century, but the physical thrust is still the exact same analog, air-cooled, carbureted iron and aluminum that trained their grandparents. The decline of Continental's American independence was a signal that the economics of the American sky had irreversibly changed. The country that invented mass-market general aviation decided that the legal liability, the environmental pressure of leaded fuel, and the cost of maintaining a sprawling analog service network were no longer worth the risk. But the engine itself refused to die. Continental taught America how to build mechanical trust. It proved that a machine could be simple enough to understand, strong enough to survive decades of abuse, and reliable enough that a pilot would willingly bet their life on its continued operation. Somewhere in a rural Midwestern hangar, an aging A&P mechanic tightens the final fastener on the aluminum cowling of a Cessna 150. Beneath the scarred metal sits a Continental O200, covered in a thin film of aviation oil and assembly grease. The machine is half a century old, the company that built it is owned by a foreign conglomerate, and the market that created it is gone. But tomorrow morning, the throttle will go in, the cylinders will fire, and the propeller will bite the air one more time. See you in the next video.